Okay, so good evening, everyone. I'm Calvin Joseph, and today I'll conduct your week 7 problem solving and doubt clearing session for this course, Control and Tuning Methods in Switch Mode Power Converters. Okay, so usually this session happens on Tuesday, but I and Teja have exchanged for this week. From the upcoming weeks, we will proceed with the same thing. Like I'll do on Tuesday, Teja will do on Monday. Hmm. So, so today we'll be discussing about these topics, that is loop gain analysis, PID controller, and what is the design for voltage mode control. And we will look into some questions. So that will so we have week 7. First we will start with loop gain analysis. Right. So in the context of control systems, because control systems is a big part of this course. So what do you have? You have a reference signal. Okay. You subtract it from your feedback signal. You get an error signal that you pass it through your controller GC of S. Then you have your plant GP of S. This is the output of your plant. You have a sensor H. And this is how you close the loop. So this is a closed loop control system. Okay, now what is the loop in this case? So your loop is this part. So this is your loop L of S. Okay, so your L of S is GC of S into GP of S into H. Okay. And what is your overall closed loop system? Like your overall closed loop transfer function, that is your Y divided by your reference. That would come out to be GC of S into GP of S upon your 1 plus L of S. Okay. So that is going to be GC of S, GP of S, 1 plus GC of S into GP of S. Now, if we assume your H is 1, that is your unity feedback, right? Then your Y upon your reference is actually your L of S upon 1 plus L of S. Okay. So this is your overall closed loop transfer function. Now, in your steady state, what do you want? You want your Y to be equal to your reference. This is your objective of control systems. That is, what does control system want? That is my reference minus my feedback or my output. That error you want to drive it to 0. Okay, so that error you want to drive to 0. So if that happens, then this is good. So if you want that to happen, your Y upon your reference is actually 1 upon 1 plus 1 upon LS. Okay. And then in steady state means your S is equal to 0. So your DC gain, that is your DC gain of your loop, is actually L of 0. And we will design this loop to have a DC gain of infinity. Okay, if that is the case, then your Y upon ref will be 1 upon 1 plus 1 upon infinity, that is equal to 1. So this is one objective, that is your DC gain should be infinite. Your DC gain of your loop should be infinite. This is one objective. So to achieve such a thing, what has Sir told in this lecture? Can anyone let me know how do we achieve this DC gain of infinity? In our loop. So I'd like to remind you.
Frequency equals to 0.
Yes, you're right. So one, you will have a pole at the origin. So your L of S will have a 1 upon S. And yes, Rahul, as you were saying, frequency equal to 0, that means since at DC I will substitute S equal to 0, this will go to infinite. Okay. So we want, like one part which we have verified now is, you want your DC gain at to be infinity in your loop. So for that you have a 1 upon S. So it is 1 upon S into some part, into some G of S. Okay, so there's some G of S. So you have 1 upon S. Now, for the what we will do is our GP of S. This is your plant. Okay, this is your plant or your system. So usually, and in this week, we are focusing on voltage mode control. So the transfer function of importance is your GVD of S. Okay, this is your transfer function of importance. So let's go to next page. So your GVD of S is given by some K DC gain into 1 minus S upon omega RHP, right? Upon 1 plus S Q omega naught plus S square upon omega naught square. Okay, this is your generic form of GVD of S. So let us start with the buck converter. Okay, for a buck converter, what we can say is your omega naught is 1 upon root LC. For your boost converter, what is your omega naught?
1 minus d by root LC.
Yes, it is 1 minus d by root LC. Now, Q is your quality factor. So, that is given for a buck converter, be R upon ZC. And for a boost converter, your Q is given by 1 minus D into R upon ZC. Okay. Any queries to this point? Achha, what is ZC? Okay. Your ZC is like you would have studied in power systems, like when they are modeling the line, the long length line, transmission line, they use this ZC, which is known as the characteristic impedance. So that you give it by square root of L by C. Okay, that is what is used to denote it. Okay, so this is ZC equal to square root of L upon C. For the buck converter, there is no omega RHP. Okay, omega RHP is not there. While for the boost converter, what is the omega RHP? That is actually R to 1 minus D square by L. Okay, this is your omega RHP for your boost converter. These are very important formulas, and I suggest you memorize them for your assignments and for your exam. Okay. There are some things you have to memorize, and this is something which you should memorize. Okay. One more thing I'd like to show is, if you do Q into omega naught for your boost converter, that will be what? It is 1 minus D upon square root of LC into 1 minus D into R upon ZC, which is what? Square root of L upon C. So this, when you simplify it, it becomes 1 minus D square R upon L, which is actually your omega RH. Okay. This is coming for the ideal case. In the practical case, it would differ. But for the ideal case, if you want to remember the formulas, everything, this is the way you should remember it. This will make it easy for you. Okay. Omega naught is 1 upon root LC for buck, and Q equal to R upon ZC for buck. But when you make it boost, you just multiply it by 1 minus D. 1 minus D in the numerator for omega naught and Q. And your omega RHP, you can get it for the boost is Q into omega naught. If you multiply it, you will get your omega RHP. Okay, so these points You have to remember. Uh, that is mandatory for you. So now, this is the closed loop system which we were looking for, we were considering, right? So we will consider now in the case of voltage mode control. In the case of voltage mode control. So what happens in voltage mode control? This is our reference. V reference is this. Okay. That we subtract with our output voltage. Okay. This is our output voltage. We use it and we subtract it. We will get our V error. Once we get our error voltage, that we pass it through a controller, GC of S. Then we have something extra. What do we have? Something extra. We have our modulator. This is our controller. This is our modulator. Then this will be our GVD of S. And this is our V out. Okay. This is our closed loop. We have, wait, I have not added the non-idealities. So I have not added the other things. What you will also have is you have your GVD of S. So there are perturbations in input that will be propagated like this over here. There will also be your Z naught, which will be which will show its effect by perturbations in your load current, which is given by I naught. And this is your overall V output perturb, okay, which comes over here. Right? So these are the dynamics for voltage mode control. So in this case, what do you think is the loop? So this is your plan. So what is the loop in this case?
GC into FM into GVD divided by 1 plus GC into FM into GVD.
Okay, that you're saying for the overall closed loop. But your loop, that is your L of S, is just this. So your L of S is actually is equal to GC of S into FM into GVD of S. This is your loop transformation. Okay. So this is the loop transfer function which we are going to shape. That is, we are going to design how we want it to look. And how do we design it? We can design it by changing our, this GC of S is what we will use to design it. Okay. So now, what is the method we use for designing? Which Sir has shown. Sir has shown stable pole zero cancellation. So your L of S is GVD of S, that is your KVC into 1 minus S omega RHP upon 1 plus S upon Q omega naught plus S square upon omega naught square. Your FM actually is 1 upon VM to your controller. Now we have to put the controller one. So controller, let us do something. K controller into 1 plus S upon omega Z omega controller 0 into 1 plus S upon omega controller 0 2 upon S into 1 plus S upon omega controller pole. Okay, so this part is your GVD of S. This part is your FM. This part is your controller. So this is your overall loop. Okay, any queries till this point?
Sir, you're considering this for the ideal converter only, right?
Yeah, yeah.
Like
For the ideal
like
converter.
uh, TCR, ECR, you're considering. Okay, fine.
If we include DCR, ESR as well, this expression of Q and omega naught only will change. Whereas the form remains the same.
Okay, fine.
So this analysis is also valid when there is a DCR, etc. When ESR is added, there comes an additional zero that I've not shown here, but that we also can see. Okay. So first I'm doing the ideal case so that it becomes simple. Okay, so now this is our loop. So can you tell me what is the order of the loop? What do you think is the order of the loop?
Two.
Why?
Oh no, sorry. 1 minute.
But why? Even if it is one or two, why? So we
Order will
just
be one. Yeah, because the degree on the top is to the power 3, and below it is,
four.
oh, it is 4. Yeah. Okay.
Okay. I don't think you can use the term degree. Let us say it is it has three zeros and four poles. Okay, three zeros and four poles. So then we say it is a fourth order system. That is, your L of S is a fourth order transfer function because it has S to the power of 4. Okay.
Fine.
Degree, I don't know whether we can use it. So that I have to check again. Okay, so now this is a fourth order system. So this is very complicated to analyze. Okay. Very easy for us to, we have studied first order, second order, third order also we don't study. So to make our life simple, what we do is we will design the controller. Assuming that we know very well what are the parameters, we design the controller such that this part and this part get cancelled. Okay, this part and this part, if they get cancelled under a very ideal case. Okay, this is a very ideal case, but it's a good starting point. So we assume that we cancel them. Maybe we had placed our controller zeros such that they cancel out this denominator of our plant. So then what are we left with? We are left with L of S is KDC upon Vm into K controller into 1 minus S upon omega RHP upon S into 1 plus S upon omega controller pole. Okay. So we have brought it now to second order form. In the case of a buck converter, there's no omega RHP, so it becomes much simpler. But in the case of a boost converter, it becomes difficult. So what we do is we place our omega controller pole to be at the omega RHP location. So it looks, how does it look? L of S becomes KDC into K controller DC gain on Vm into 1 upon S into 1 minus S upon omega RHP upon 1 plus S upon omega RHP. Okay, why didn't we place our controller with 1 minus is because we cannot, we should not. It would result in some, as sir had mentioned, some internally it will become unstable. Okay, so that we don't do. So we place our omega controller pole in coincidence with our omega RHP. So what is the benefit of this? What do you think will happen?
The omega RHP will get cancelled.
Omega RHP
That
is not getting
0 will
cancelled.
get
It's there.
cancelled.
Magnitudes will get cancelled.
Yes. The what we are trying to do is like the magnitude contribution of the omega RHP of the right half plane 0 that we are trying to nullify it. Okay, we don't want it to affect so much. So we place our controller pole at that point only. So if you will see if you just consider this magnitude of this, its contribution of magnitude in terms of magnitude is only 1. Okay, in terms of magnitude, this contribution is 1. But in terms of angle, this contribution is minus 2 tan inverse of omega upon omega RH. This is the phase contribution of this term. Okay. So the magnitude contribution of this term is 1, but in terms of phase contribution, it is given like this. So that affects our phase margin. Okay, that will affect our phase margin. So if you will see the magnitude contribution of this, it is KDC into K controller Bm into omega. This is our magnitude. When we see the angle of L j omega, that will be your integrator will give rise to minus 90 degrees. It is a fixed minus 90 degree. But these two will result in minus 2 tan inverse omega upon omega RHP. Okay. Now, what is phase margin? What do you remember from the term phase margin? And why is phase margin important? Any idea?
180 plus phase angle at the gain crossover frequency.
Okay. So your phase margin is 180 plus the angle of this when your omega is equal to your omega crossover. Okay. So what is the significance of this?
Phase margin should be positive for a stable system.
Okay. So your phase margin should be positive. So it is like the degree of phase lag which you can still provide in your system so that it maintains stability. So if you want it to be stable, you have to have more phase margin, higher phase margin. Okay. And what happens is in your practical system, when you will implement and other things, they will come delay. So what the delay does is delay will not affect your gain plot. Delay will affect your phase plot. Okay, so delay to anticipate that delay, the phase lag, your sensors also may have phase lag. All that's why you have to have some good amount of phase margin. Usually they select 60 degree, 45 degree, etc. Okay. So if you do phase margin over here, you will get 180 minus 90 minus 2 tan inverse of omega upon omega RHP. That is 90 minus 2 tan inverse of omega upon omega RHP. Okay. So this is how you will shape the loop such that you will get a phase margin. Achha, I'm sorry, this will be at omega C, omega C. Now, how do we select our omega C? So omega C comes from our bandwidth. What bandwidth we want. And when your angle of L, J, omega C is there, it crosses 1. Value becomes 1. So that would mean your KDC into K controller upon Vm into omega C is 1. So from this, you get your expression of omega C is equal to KDC into K controller upon Vm. Okay, so you have two things. Either you can select phase margin and then you will get what bandwidth you want, you will get, or you set the bandwidth you want and then you will get your phase margin. Okay, so there are two ways you can do. And that is, sir has shown some MATLAB code, etc. for you to do that. So any queries still here? Okay. So I'll proceed with what is known as a PID. PID controller. So what do you mean by PID controller? What is its full form?
Proportional integral derivative
Yeah.
controller.
This proportional integral derivative. So this controller has a proportional part, has a 1 by s part, that is your integrator. It has a kd of s, that is your derivative. But you cannot actually physically realize such a derivative. So what is there is we have a filter, 1 plus tau ds. Okay, this filter frequency can be set as per our requirements. Okay. So when you get your overall system, you will get it in terms of some ki into some 1 plus k1s plus some k2s square upon s into 1 plus tau d of s. So how many poles it has? How many zeros it has?
2 poles and 2 zeros.
Okay, so there's two poles, two zeros, and one pole is at the origin, right? So that pole is required for you to set the DC gain to be infinity. Okay, so that is what is done. So now we'll proceed to our questions. Let us start question 1. Question 1. Okay. Okay, so I'm considering a boost converter. Input voltage 12 volt, output voltage 30 volt, load resistance is 30 ohm. Inductance 3.3 microhenry. Output capacitance 50 microfarad. Switching frequency 200 kilohertz. And it is operated in voltage mode control with a ramp voltage VM of 2 volt. So you have to design it using pole zero cancellation. Okay. So what should be done? What is the method? So which controller should be used to compensate the loop? You can tell your answers.
PID controller.
Yeah. PID controller can be used. Hmm. Yeah, I forgot to mention one point is so sir had mentioned something known as a type 3 compensator. Okay. So what is a type 3 compensator? Type 3, it also has some controller DC gain. Okay. Into 1 plus S. It has two zeros and it has three poles. It has two zeros and it has three poles. Okay. So if it is the generalized form and PID controller is a special case of type 3 compensator. If we set one pole to be infinite in the case of a type 3 compensator, then you will get a PID controller structure. Okay. So this is used when we have a practical boost where we want to compensate for the effect of the ESR. Equivalent series resistance 0. If you want to compensate or cancel it out, we need this additional pole. Okay. So type 3 compensator. Let's go to the question. So question 1, we have voltage mode control. There is a boost converter, right? It has input voltage is 12 volt, output voltage is 30 volt, L is 3.3 microhenry. C is 50 microfarad. Your load resistance is 30 ohm. Switching frequency is 200 kilohertz. Okay. So this is the steps I follow while solving sums. I recommend you guys use this method, but it's up to you because uh, I like to write what is given in the sum, so that second time I don't need to go back to the sum. Okay, this would be useful for you in your exam. So what we need to find is which compensator. As you have said, we will use a PID controller for this. Okay. Next is they ask what is the duty which is required. So what is the duty for this boost converter? What is the value of duty required?
One minus 12 by 30. 1 minus 0.4, 0.6.
So duty required is 1 minus 12 by 30. So that is 1 minus 0.4. That is duty is 0.6. Okay, so this is the duty which is required. Next, what they have asked is what is the quality factor and natural frequency at this operating point? And what will be the desired value of Kp, Ki, and Kd? Okay, good. So they asked what is Q, what is omega naught, and we have to design the PID gains. These are required. Okay. So what is your Q? What is the formula for Q for a boost converter? Let us go with omega naught first. What is the formula of omega naught for a boost converter?
1 minus d by root under LC.
Okay, 1 minus d by root LC. So what is that value? You guys don't have calculator.
Uh, 31.14 into 10 raised to 3.
Okay, that is 31.14 into 10 raised to 3. Okay, now what is your Q? Q is R into 1 minus d by ZC for boost. And that is R into 1 minus d square root of C by L. So what is this value?
.71.
So your Q is 46.71 ohm. Not ohm, it's 46.71. So, will this system be underdamped, overdamped, or critically damped?
Theta we need to find.
Okay. So what is the relation between Q and zeta?
Two
Uh,
epsilon
2
uh,
omega 0.
Mm-hmm.
2 zeta omega 0 will be equal to 1 by. We can convert this into standard format, s square plus 2 zeta omega ns plus omega n square.
Yes. Okay.
Then compare the terms, so we will get expression for zeta.
Okay. And Rahul also saying something?
Yeah, that's what, like 2 zeta omega naught equals to 1 by q omega naught.
Yes. So your Q actually is equal to 1 upon 2 zeta. This is the expression. Okay. So what would be your zeta in this case then?
Q.
One by 2 into 46, so it is less than 1. So under damped.
Underdamped.
So it is an underdamped case. Okay. And then like you to note the zeta comes out to be around 0.01. So it is severely underdamped. It is very underdamped. If you will see the overshoot and all, it will be lots. It is very underdamped case, right? So that's why it is very difficult to control a boost converter in voltage mode control. Okay. Also, the meeting will end in 1 minute. I will once the meeting ends, I will restart the meeting on the same link. So you just have to join in the same link. This is your zeta we got. What is left is omega RHP. Omega RHP for boost we saw it is Q into omega naught. So how much is that?
1.45 into 10 power 6.
Okay. Now we have got this omega RHP, we have got Q into omega naught. So what we will do now is we have to use PID controller. GC of S is Kp plus Ki by S plus KdS into 1 plus tau ds. Okay. So we'll simplify this. So you will get it as Kp into S into 1 plus tau d of S plus Ki into 1 plus tau d of S plus Kd into S square S into 1 plus tau ds. So that when you open it, it becomes Kp into tau ds square plus Kps plus Ki plus Ki tau ds plus Kds square upon S into 1 plus tau ds. Okay. So that becomes equal to Ki plus S into Kp plus Ki tau d plus S square into Kd plus Kp tau d upon S into 1 plus tau ds. So that we can write, we want to find a DC gain. If you want to find a DC gain, we write in a normalized form, we take Ki common. So we get 1 plus S into Kp plus Ki tau d upon Ki plus S square into Kd plus Kp tau d upon Ki. This into S into 1 plus tau d of S. Okay, so we have got till here. So now what do? We will do what is known as pole zero cancellation, right? Where there's a plant, I'm not written my plant. GVD of S is KDC 1 minus S upon omega RHP into S into 1 plus tau D of S, right? Sorry. 1 plus S Q omega naught plus S square upon omega naught square. Your GC of S is so ki 1 plus k1s plus k2s square upon s into 1 plus tau ds. This is our controller, this is our plant. So now we want to find the loop. Okay, so let us find the loop. So your loop transfer function is GVD of s into G3 of s into your modulator gain Fm. And your Fm is what? 1 upon Vm. Okay. So you will get it in the form of KVC into 1 minus s upon omega RHP upon 1 plus s upon q omega naught plus s square upon omega naught square into 1 plus into your ki into 1 plus k1s plus k2s square into s into 1 plus tau ds into your 1 upon bm. Okay. So as we had discussed earlier, what do? We lump the DC gains, this KDC into KI upon VM, that multiplied by 1 minus S upon omega RHP into S into 1 plus S upon omega RHP. Now what do? We do cancellation. We cancel this and and we replace our tau D by 1 upon omega RHP. Okay. So now, in this case, what I get, my K1 is equal to 1 upon Q omega naught. My K2 is equal to 1 upon omega naught square. Any queries in this part?
No, sir, it's clear.
Okay. So, what is my K1? So, I'd like to tell my K1 is Kp plus Ki tau d by Ki. Okay. So, my K1 is equal to Kp plus Ki tau d, Kp plus Ki tau d by Ki. Okay. So, that is equal to Kp by Ki plus tau d. But your K1 is 1 upon Q omega naught, which is equal to Kp upon Ki plus 1 upon omega RHP. And as I discussed, Q omega naught in the case of ideal buck is omega RHP. So these two again get cancelled. So this implies your Kp is equal to 0. Okay, so we have got our Kp equal to 0. Now, in the second case, we have K2 is equal to 1 upon omega naught square. And what is your expression of K2 is Kd plus Kp tau d by Ki. So this is Kd plus Kp tau d by Ki. Since we have already found that Kp tau d is Kp 0, so this becomes equal to Kd by Ki. So your Kd is equal to Ki upon omega naught square. So now we have to find both Kd and Ki, but we have only one equation. What to do now? Call all the experts. HP, Parvati, Rahul, Karun, what do you think we should do?
Phase margin.
Okay. So there is something known as phase margin. Okay, good. So what was the question? Say phase margin. I have not mentioned it. Okay. phase margin was not mentioned. We'll take some, assume some value. But first, what I'd like to point out to you guys is this is your expression of L of S. Okay, this is your L of S. So I want to find what is the magnitude of this. So what I would do is let us do the magnitude of Lj omega. That is your KDC into your Ki upon Vm into omega. This is your magnitude because as we had told, this magnitude contribution is 1. It gets normalized. It gets cancelled out in terms of magnitude contribution. And in the case of angle of Lj omega, it becomes equal to minus 90 minus 2 tan inverse of omega upon omega RHP. Okay, these are the two values which we get. So now, what do we assume? We have, and this actually will be your, and your Lj omega C is equal to 1. So your omega crossover frequency is KDC into Ki upon Vm. Okay. Okay. Now we know your phase margin is what? 180 plus angle of Lj omega. Right? Omega crossover frequency. So we write it as phase margin is equal to 180 minus 90 minus 2 tan inverse of omega C by omega RHP. So that is equal to 90 minus 2 tan inverse of omega C by omega RHP. Okay, answer is told that if your omega C is equal to omega RHP, then your phase margin is 0. That is not a stable design. If your omega C becomes greater than omega RHP, the assumption is not a stable design as your phase margin will then be negative. So we want our phase margin to be positive. So what I would consider is, let us say our omega C is equal to omega RHP by root 3. We take it to be a fraction of that, right? So what do we get our phase margin in that case to be? Phase margin is equal to 90 minus 2 tan inverse of omega RHP into 1 upon root 3. Okay. So what is tan inverse of 1 upon root 3?
30 degree.
30 degree. So it becomes 90 minus 2 into 30. So phase margin comes out to be 30 degree. So is this a good design?
Yes, positive. So it's good design.
But phase margin 30 degree is a little bit less. It's a little bit less than what we usually prefer. We prefer phase margin of 45 degree to 60 degree, but okay, let us assume our phase margin is 30. Anyway, we are just designing analytically. So we have assumed phase margin 30 degree. So what do we get? Our omega C is equal to omega RHP by root 3. Right? This is our crossover frequency. Now, let us see what is the expression for omega C. Omega C is KDC into Ki upon Vm. So omega C is KDC into Ki upon Vm. So your Ki is equal to omega RHP by root 3 into Vm upon your KDC. Now, we have in the question, it was mentioned that a ramp voltage Vm equal to 2 volts. So we have this 2 volt we have. Okay. Sorry. Omega RHP also we have, but we have PM also. KDC we don't know. So what do you think will be the value of KDC in the case of boost converter? KDC is the DC gain of GVD.
V in by 1 minus D square.
Yeah, correct. So when you guys are answering, you're answering with lots of fear, I suppose. Here I can sense. Okay. So your KDC, it is actually equal to 12 upon 0.4 square, right? So now we have to find Ki. So Ki omega RHP, what is omega RHP? That is where is it going? Omega RHP is 1.45 into 10 to the power 6. So you have 1.45 into 10 to the power 6 into Vm is 2, square root of 3 into 12 upon 0.4 square. So what is the value of this?
(22.32 into 10 raised to 3).
This comes out to be 22.32 into 10 raised to 3. Okay, this is what we got Ki. Now we have to finally find our Kd. This is the expression for Kd. We got Kd is Ki upon omega naught square. So Kd is equal to Ki upon omega naught square. So this is 22.32 into 10 to the power 3. What is the expression for omega naught? We have calculated. So I think omega naught is equal to 31.14 to 10 to the power 3. Yes, 31.14 into 10 to the power 3. So what is this value?
Uh, 2.3 into 10 power minus 5.
So that becomes equal to 23.02 into 10 to the power minus 6. Yep.
Sir, we proceeded with omega C is equal to omega RHP by root 3. But for an ideal good design, what should be the condition? Should we equate phase margin equal to 60 degree and recalculate omega C?
Yeah. That would be better. In the question, it would be provided. In this question, I was making it in a hurry, so I couldn't. I didn't decide the phase margin. Okay, but you can do accordingly.
Okay, sir.
It will be mentioned in the question. Which you have. Okay. So this is. So I'd like you when you are giving your exam. Like I have not given NPTEL exam. So what does it happen? Like, is it like fully like gate type of exam? It will be there, or how is it?
Usually it is gate like multiple choice questions. In some subjects, there will be pen and paper exam, but it will be already mentioned. Here it is, I think, MCQ for this course.
Yeah, this one is MCQ.
Sir,
Like,
all type of questions are here, not just MCQ. MMCQ is there. Number type answers are there. Match the following. Those are all are there.
yeah. Those also are there.
That is also the numerical answer type was also there in some subjects.
Yeah,
We have to type and enter the values.
I think in this subject also it would be there. Would be there, okay? Because you tell
Yeah,
me the
here also we've seen some assignments.
yes.
Yes.
That is there. Yeah, and I was also getting some complaints that people are not able to solve the assignments. Someone has messaged on YouTube that assignments are not getting marked or something. Is that true?
Yeah, last assignment was very difficult. Yes.
Okay,
So
okay. Achha.
assignment 6, I
Six.
think it was extremely. It was, yeah, quite
Okay.
difficult.
Mhm. Yeah. Well, not wrong. I actually don't know the marking, complete marking scheme. Mhm. But in the question paper, which would be given to you, like what I remember, like assignment questions similar to that, like 50% of the question papers like that. Then some recall questions like where you have to remember things. So recall also is there. Okay, so there is weightage for recall. Recall means you have to remember. So that means some formulas, important formulas, you have to remember. You're graded for how much you remember. So that I think is 30% and 20% is like open. There's like some questions which are based on this topic. Okay, like that. Yeah. So that
Sir,
is yes.
sir, one at the end of the course, whether we will get the fully solved assignment problems. This is the first time I'm attending a NPTEL course, so I don't know. Because I've heard that at the end of the course, all the assignment with the proper answers we will be getting, so that we can refer that.
I don't know about that this happens. I don't know whether you will get for this course. I'm not sure actually. But no,
Yeah,
no,
for
you.
the other subject, they are releasing week by
Yes,
week,
yes,
like
yes,
the
yes,
previous
yes.
week's assignment. They are releasing that.
Yeah, yeah.
Not
Yeah.
in this course, but in the other courses. They are doing that.
Because I remember like the last course also, which I took, after we get the after we get the grade, when we get the grade for the wrong and for the correct answer, we tell what is the step. I think here it's not done actually. That is something which we have to look into. Okay. So have you guys raised that query on the portal or the Q&A?
No, sir. Actually, I heard it from my friend that they got last time when they attended NPTEL courses, they got the assignment fully solved. So they referred for the different problems in that one. So that's why I'm asking. I don't know about this course.
Okay, okay, yeah, yeah, yeah. So I think you can raise a query in the Q&A and all that, and you can ask. Because that would make it very easy for you all. And just refer to that and learn.
Yes, sir. It will be helpful for preparation of exams. That's why I'm asking.
Yeah, yeah, yeah. And apart from that, like, what is like, do you find difficult in the assignment? Like, as a general feedback, it's difficult. It takes time.
Yes, sir. Difficult.
Okay, okay. Difficult is a very
Just specifically the MMCQ type of questions, like more than one option. Like
okay.
sometimes it's two, sometimes it's three, sometimes all four are correct. So
Okay.
that's one
Yeah, that is difficult.
slightly difficult.
So there we are. The focus is mainly like they are testing your knowledge. So match the following is simple, but when you have multiple correct things, but what is it like? If you get two options correct and one option wrong, also you're not getting marks or what?
Partial marks we're getting, like if we select the like wrong
Correct
option
option.
which is not included, then completely the marks is gone. Yeah, but if you
Hmm.
select two, let's say three of the correct answers, you select two, then
Okay.
you're getting partial marks.
Okay. Okay. Yeah. I don't think those will come in the exam. And with multiple things, I don't think it will come in the exam. But shouldn't be an issue. Then MCQs. numeric answer type, I want you to be careful like regarding this. Like if you see over here, that's why I'm specifically writing 10 to the power minus 6, 10 to the power 3. And in case it was like time or seconds, units, then you must see whether they're microsecond, millisecond. Those things also you must watch out. In that case, they will not say 10 to the power minus 6, 10 to the power minus 3 or something. Huh? So those units also you have to see. You have to be careful for numeric answer types. And yeah, like this sum is a lengthy sum. This sum which we did is a lengthy sum. So such sums you keep for the last, keep for the end, right? This is what I wanted to know. Are you able to see all the questions at one shot when you're giving the exam, or do you get one question at a time?
I believe one at a time, but yeah, we can like mark it
We
for
can go to
review and come back to it later. Yeah.
Okay,
on the right side. There will be something like a palette 1, 2, 3, 4. So we can click on that question and go to that.
okay. So it's not like once attempt and you just use it, not like that. You can mark it for review, right? Then it's good. Yeah.
Yes,
So
yes.
that's what. So difficult questions, you just mark it for review and leave it. And solve the easy ones first, mark them properly, carefully. Then you come back for mark the ones which are marked for review. And as I said, what I prefer is I write down what is given. It makes it easy for like if I marked it for review and I come back, I don't need to read the question again. I've already written what is needed for me to solve. So that makes it easier. And you'll be getting papers, right? The rough sheet. So you could, I'd say, make it into like you could go in a sequence, so that if you want to come back to what question you have written, some given and all that, it is in a correct sequence. So you don't do randomly. Don't go randomly. That's the thing. And in the cases where certain sums, they don't mention your ESR, they don't mention your inductive TCR, they don't mention your switch on resistance, you assume it is the ideal case. Okay, you assume the ideal case. The next type is there are given your parasitics, the on resistance is given, ESR is given, inductor DCR is given. Okay. Then you check whether it is a numeric answer type question or it's a multiple choice question. If it is a multiple choice question, what you do is you just calculate the Q and omega not assume, you just calculate it for the ideal case. Then you correlate with then you check in the options which answer closely matches with that. Because when you add the parasitics, all that, their contribution is negligible. So this 31.14 might become 30.04 into 10 to the power 3. But it is 30 into 10 to the power 3, right? Your next option might be 45 into 10 to the power 3, 100 into 10 to the power 3, 1 into 10 to the power 3. But you know it is coming around 30 point or 31.4. So you know what is the value. You know what is the option. If it is numeric answer type where you need to get the exact value, then you have to find it for the practical case. But in the case where it is it is a multiple choice question, you just calculate it for your ideal case and see whether the options are close to that. That would make it simple. So you don't need to go derive for the entire parasitic case, etc., and get it. Okay, just start with the ideal case. If the option matches, it is good. If it doesn't match, then you can come later and you can spend time on that. Right. And certain questions will have hints. They will have hints. So you be very careful to check that hint. The hint you must see carefully. And the questions, sometimes what you do, they bunch the questions together. That is, you have question 20 to 22 are in a sequence. So you have to first solve question 22. Based on that, you will solve question 21. Based on that, you will solve question 22. So you see what is the form of the question very, very carefully to see what are the forms. Okay. So those are certain tips, and I hope they'll be useful, and I hope you'll all do well. So I guess all of you have signed up for giving the exam, or some of you are just seeing it?
Yes, sir.
I have signed up. Yeah.
Okay.
Yes, sir. Yes.
Yeah. Then it gets difficult. But yeah, you can do. Because then only you will get the certificate, right?
Yeah.
Yes. Yes.
Like overall 40% we have to get like assessment and exam combined. So yeah.
Yeah. Yeah, don't worry. Yeah. That's hopefully
Yes.
half of the course. Yeah, and MATLAB based things you don't have to do. Like you will not have to simulate many things in MATLAB which is done. Those things you don't have to do. You just have to know the basic and work on them. Yeah. That's the,
So
okay.
where I have to write the query regarding that assignment answers,
In the
where I have to.
Q&A, in the NPTEL, the Q&A section is there, na, where the Q&A forum, it goes to a different, like a kind of like a Google group or something. Somewhere.
Okay, sir.
There. Okay, we'll proceed to the next question. Yeah. So, how will you solve this question? So, what they have told, we have to design a controller. And which controller should I use for this case?
We can have two zeros for the controller to cancel that S plus 50 and S plus 200.
Okay.
Then a controller pole at origin and another pole at say S plus 10, like S plus 10.
Okay. So, we'll do that same approach as we have done.
PID will only work. Yeah.
Yes. Yeah, give me a So, we'll go for question 2. The GVC of S is given by 10 minus S on S plus 15 to S plus 200. Okay. Now we have to design a controller. So we will design the zeros to cancel the plant poles. Then we design it as an integrator. You should be there to get your infinite DC gain. And then we place our pole in coincidence with your RHQ 0. So what? So and then what should I do?
But phase margin equal to 60 degree also we need to.
Yeah. So how do I make sure that what else? Some other factor I need to add. What is that?
Controller gain.
Yes, exactly.
KI into.
So yeah, so your controller gain. So now my loop is what? GC of S into GVC of S. So that becomes equal to your K controller on S into 10 minus S on S plus 10. So again, the magnitude is K controller by omega, and the angle of L of J omega is equal to minus 90 minus 2 tan inverse of omega upon 10. Any doubts in this part? Because let me elaborate this because I think I'm rushing through it. Let me do step by step. L of J omega is K controller by j omega into 10 minus j omega upon 10 plus j omega. Okay. So now your 10 let us start with 10 plus j omega. 10 plus j omega, this is in the xy form. Let us write in the radial form. That would be 10 square. This is the magnitude plus omega square, right? And the angle of this will be tan inverse of omega upon 10. Okay, this is the angular contribution of this. Similarly, 10 minus j omega, that again is 10 square plus minus omega square is plus omega square. It is same. And the angle contribution of that is tan inverse of minus omega by 10. Okay. And for j omega, what is it? Its magnitude contribution is omega and its angular contribution is minus 90 degree. Okay. So now,
Sir, is it plus 90 or
oh, we have plus 90, correct. Plus 90. Because it's in the denominator, then it becomes minus 90. Good. Thank you. So now, my L of j omega, I write it in terms of the magnitude of it and the favor. Okay. So, that's how I write it is K controller upon omega the square root of 10 square plus omega square upon square root of 10 square plus omega square, right? Into the angular contribution. Let us write angular contribution. It is not exactly multiplication. It would be written as angle. Okay, so that is equal to what? 10 minus j omega, that is tan inverse of minus omega by 10. That we can write this minus tan inverse of omega by 10. Okay. Now j omega is in the denominator, so it becomes minus 90. And again, this is in the denominator, so it becomes minus tan inverse of omega by 10. Okay. So these two terms are the same. That's why by L of j omega is equal to K controller upon omega into the angle of minus 90 minus 2 tan inverse of omega by 10. So this is how you represented your loop in terms of its magnitude and in terms of its phase. And this equation is valid for any frequency, right? Because it is in terms of omega. It is in terms of omega. Now, this I'm just explaining this because these things, some of you might have doubts. So I just want to show this to you so that accordingly in the various other next controllers which you will all design and everything, you can know that these are the steps. These are some steps where you should be very careful not to make any mistake and make any errors. And once you solve these kind of sums multiple times, you don't need to do these steps. Like these steps I'm doing just for reference. But I knew it is given by this experiment because I've done it multiple times, right? So slowly you can get that speed, but that speed will come by practicing it yourself. Okay, you have to practice it yourself, not like look at a solution or look at what someone else has done, something. It's best if you do it on your own. Like you study best when you close your book, don't refer anything and just write what you remember. That is very, very useful. Okay, because it forces your brain to slow down and it will show what you understood, what you didn't understand, what you remember, what you don't remember. That's the best way to learn. That's the way I find effective. You can have other ways as well. I don't know what works for you, but this is what I recommend. Okay. So now, what we want is our magnitude of j omega, K controller upon omega, and our angle of L of j omega is minus 90 minus 2 tan inverse of omega by 10. So your phase margin is what? 180 plus angle of L of j omega. So that is 180 minus 90 minus 2 tan inverse of omega by 10. So that is equal to 90 minus 2 tan inverse of omega by 10. Okay. So we have got this. So now we had wanted the phase margin to be 60 degree. So if you want your phase margin to be 60 degree, this is 60 equal to 90 minus 2 tan inverse of omega by 10. So what do you get? You get your 2 tan inverse of omega by 10 is 90 minus 60 is 30. So tan inverse of omega by 10 is 15 degree. So what do you get your omega to be?
2.679.
2.679. Okay. So your omega, this is your crossover frequency. Okay. So this is 2.679. Now what is left for you to design is your K controller. So you know your magnitude of L, J, omega, C at the crossover frequency, that is equal to 1. So that is given by K controller by omega C is equal to 1. So this implies your K controller is equal to 2.679. Okay. So that's how we have designed our controller GC of S, which is K controller into your S plus 10 into S plus 200 on S into S plus 10. One of it is missing. It is S plus 15. S plus 15. If this is given by S plus 15. So this K controller is 2.679. Okay. So till this we have done. So I'll proceed for the next question. Given here. So can you tell me which of the following are true regarding the practical PID controller?
Sir, A, B, and C.
Yeah, correct. What's the issue with D?
They are not the same, like PID and type 3.
Okay. Okay, that's good. Actually, HP, there are no sample questions to solve actually. So assignments and these questions which I'm solving in the sessions as well as what Teja is solving, that you refer. Okay. Because we also, I and Teja also are preparing our own questions. We are not referring to any book. Acha, one more thing I'd like to suggest for you all is share say this link. Is that we have been given to this, you have to refer to this. Okay. This is a very, this is a paper by Sir. I'll just share the link to you guys. Take it up. So I'll just open this. It is very huge, so you don't need to read it. Just you can see the important topics which you could refer. Right? So this is like open access. Okay, it's in the open journal of power electronics, so you can download it even if you have IEEE access or not. It's taking time. Okay, it's taking time. Let's proceed to the next question, Tilda. Okay. What do you think is reducing the phase margin?
So previous question was ABC only, right? Like,
Yeah, correct. ABC only. Yeah. Type 3, sir,
fine.
has an additional pole. PID doesn't have that additional pole. So you can modify a type 3 into a PID, but you can't change a PID into a type 3.
Okay.
So for phase margin, what do you think? I'll just come in 2 minutes. You guys just see this question.
Sure.
Okay. So what do you think
Sir,
reduces
A, C, and D.
ACL?
D.
Okay, what reduces the phase margin? Okay, all right. Why is this? What about others?
Sir, in the previous problem, we got the expression like 90 minus tan inverse similar omega by omega RHP. So omega RHP is affecting phase margin.
Okay, good.
Then omega also depends on that DC gain
Okay.
from the expression of. So
Uh,
those two are affecting.
okay. So how I'd like to look at this question is question 4. You have your GVD office, right? That is for a boost converter I'm considering. That is Vn upon 1 minus D square into 1 minus S upon omega RHP to your 1 plus S upon Q omega naught plus S square upon omega naught square. Similarly, you have your modulator gain that is equal to 1 upon Vm. Okay, let us assume we are not that bothered of our controller. Let us assume we have designed our controller and the controller doesn't change. What we are worried about is your GVC office. That is your control to output transfer function. That is equal to your Fn into GVD. Okay. What is that given by? That is equal to your V in upon Vm into 1 minus d square into 1 minus s upon omega rhp upon 1 plus s upon q omega naught plus s square upon omega naught square. Okay. So notice in the question I was focusing a lot on your DC gain. That is what and all are coming. I'm talking about the input voltage, the Vm, right? And your overall, this overall thing is your DC gain. Okay, this overall thing is your DC gain. Now, this is fixed. Okay, this is fixed. So this magnitude also has some impact. The phase also has some impact, and that impact does not change. So your plot let us assume this is your body plot, right? This is your body plot, and it crosses zero at this point, right? And at this point, you have certain phase. Let us say plus, let us say it is minus 60 degree. I think for this, it will be better if I do MATLAB. MATLAB would be better to understand this. Let us go to MATLAB and try it. Okay. Need say that. We have G underscore V. Let us say define transfer function S is equal to transfer function S. GVD is equal to G underscore DC to okay. We define omega RHP is R into 1 minus 2 raised to 2 by L. Or let me take it as 30. Omega naught is equal to 1 minus D by square root of L upon C. No, it is square root of L into C. L into C out, I define C as C out. And your Q is equal to 1 minus D divided by square root of L upon C out. L divided by C out. And this is the expression. S equal to transfer function of S into 1 minus S upon omega RHP divided by 1 plus S by Q into omega naught plus S upon omega naught raised to 2. It is a transfer function. Let us run this section. So this is the transfer function which we get. Okay. So now, okay, there's a transfer function which we get. Let us do the ZPK 3D. Okay. DC again is 5,000. These are this is the way you have. Okay, this is the fine. So this correct. So now what we will do is figure 1. Let us do the body of GBD. Right? So this is the body plot, right? This is the body plot which we get. Now, Okay, we can do characteristics. We can see the stability margins. We see this over here. It is showing unstable. It is showing unstable. Open loop, it is unstable. Showing unstable. So what? So open loop, it is showing unstable. If we close the loop without any compensation, it is showing unstable. What we will do now is we will add your RAM, that is 2. So let us say 10. And your FM is equal to 1 upon 10. Now you will add our bode GBD into FM. Hold on. Let's run this. Okay. Okay. Fine, fine. So your phase remains the same. But now what has happened? It has become stable. Why it has happened is because I have made that ramp voltage to be high. When your ramp voltage is high, this DC gain of this gets changed, it becomes lower. And then finally, where it crosses this one, this zero, that is at that point is your crossover frequency, and there the phase is less than 180. If the phase is less than 180, it is stable, it will have a positive phase margin. But in the case of your original plant, right, in your original plant, it was crossing zero when your phase was more than 180. Okay, so that's why its phase margin was negative and it was unstable. So now what I'd like to do is, what I'd say is if you change your input voltage, assuming you don't change anything else, there could be a condition where let us change our input voltage. Let us change input voltage. Let me make input voltage to be 10. Now, how does it look? So as I change my input voltage, again the response changes. So if you see in this small area, in this small part, it is getting shifted. It is getting shifted. So that's why change in input voltage can affect where it is crossing. Where it is crossing, it can affect. But it is not exactly clear whether if you change input voltage by this much, your loop will change this much. That point is not exactly clear. In a buck converter, it is very clear. In a buck converter, what happens? If you change your input voltage, your DC gain will go up and down, up and down. But in the case of your boost converter, it is not exactly straightforward. This is one point. Similarly, so is this your VM. Your VM, if it is more, if your VM is more, then this DC gain gets shifted lower. And when this DC gain gets shifted lower, your phase margin becomes positive. Okay. So if you want it to be stable, you have to, what you have to do, you have to increase your VM, you have to reduce your V input, right? Your omega RHP also has an effect on your phase margin. And what else was that question? Let us see. A smaller DC gain. If your DC gain is smaller, that is effectively you're making this part smaller, then your phase margin would be better. It would be better because the phase contribution remains the same. Are there any doubts in this or should I explain again?
Sir, once more, can you just explain, please?
Okay. Okay. Let me just browse on all this. So the blue curve is the open loop transfer function, GVT plot. And this orange curve is your GVC plot, control total transfer function, where it is multiplied by a gain of 1 by 10. So ignore all those things. Just look at the phase plot. If you look at the phase plot, it is always, okay, why is it starting from 360? Let me change it. Sorry. Properties should start from 0. We'll go. Grab this phase also. Okay. So your phase is starting from 0. Okay, just start. Okay. So your phase is starting from 0. Then when your double pole comes, phase falls rapidly, right? And it goes on. Okay. So the phase plot is same for both the transfer functions. But if you see the DC gain of the second one, this orange one is less than the DC gain of your blue one. And when you will see statistics, let me show all stability margins. You can see this one is stable, while this one is less stable. Why? Because the DC gain of the first one, of the second one, that is the orange one, was lesser than the DC gain of the first one. So if you want a higher phase margin, in this case, you would need the DC gain to be less. DC gain to be less. That's why I said you would want a smaller DC gain. High input voltage also would reduce the phase margin, because what would happen, your DC gain would become high. High sorted voltage will reduce the phase margin because your DC gain will go lower. So what variables reduce the phase margin? Your sorted voltage reduce the phase margin. DC gain also will reduce your phase margin. And your RHP0 will have a negative phase, so that also will reduce your phase margin. Okay.
So ACD is the answer.
Yes, yes, ACD is the
Input
answer.
voltage has no impact.
Input voltage will no. Wait, what
Increase the
reduces
phase
the
margin.
input voltage will increase the phase margin. No.
Fine, okay.
Wait. I'm thinking and making an error. What reduces the phase margin? Your input voltage, when it is higher, it will reduce your phase margin. And when your DC gain is smaller and when your sorted voltage is higher, that will increase your phase margin. Okay, so let me write it down. I'm also getting confused. Let me write it down. So if your Vin increases and your omega RHP also comes closer, your phase margin will reduce. But if your VM increases and your DC gain gets lower, then your phase margin will increase. Okay.
Sir, is it like when the loop gain increases, body plot will move upwards? So gain crossover frequency will increase and the phase margin will decrease.
Yes,
If
exactly.
we decrease the gain, body plot will come down and the gain crossover frequency will move leftwards and the phase
Yes.
margin will increase.
Yeah. Correct. Yeah. So this is considered like the open loop case. When you do your closed loop, what you do is, what happens is at this point itself, let us say your frequency is like 8.96 into 10 to the power 4. At this point itself, it is crossing your 0 around this point. So what you try to do is, your controller will try to give a boost. It gives a boost to the phase such that it will cross this minus 180 at a later point. And you give us, accordingly, you will adjust the gain as well, right? So that adjustment is done by a compensator or controller. What is it? That's what we told you, loop gain analysis. That is, you will adjust the loop in such a way that these phase margin will be your 60 degree, 30 degree, what you want. And your crossover frequency is also designed for a higher value. Okay. So that your response will be fast. So I proceed with the next question, the last question for today. This is also a very simple question. So I have given a buck converter. I want you to find you can find the GBD. For finding GBD, you need to calculate Q factor and natural frequency. So what are those values? Let me know. So what is the formula for Q? Let me write here.
R by ZC.
Yes. So question 5. Buck converter. You go to R upon ZC. That is R into square root of C by L. Your R is 1, C is 5 millifarad, and L is 220 nanohenry. So what is this value? Q comes out to be 150.75. What is your omega naught? That is 1 upon root LC. What is that value? So your L is 220 nanohenry and your C is 5 millifarad. So what will be the value of omega naught?
Sir, R load is 10, right?
No, R load is 1. R load is 1 ohm.
Oh, okay.
Okay, what value did you guys get for omega naught, which is 1 upon root LC?
30151, 30,151.13.
30,151.1 something. Okay. Now, the final part of the question is, what is the steady state operating point? Now, I want you to find out what is the steady state operating point. You know your Vn is 12, your Vref is 1 volt, your R is 1 ohm. So, what would be your V output? What would be the value of the output?
1 volt.
Your V output should be 1 volt. And what should be your IL, average steady state value?
Same as I0.
And what is
So
your
1
I0?
ampere.
So I0 is Vref upon R. So that is 1 ampere. Okay, that is your steady state value, right? Now, in case there are certain parasitics, then these values just change a little bit. 1 volt may become 0.98 volt. 1 ampere may become 0.99 ampere, but in a slight small value. Okay. So I again recommend get the ideal case values. If you really want to be accurate and if the question demands that you should be very accurate, then tweak it for the parasitics. If not, go with the ideal case. Yes, sorry. Okay. Okay, so are there any queries regarding all this?
Sir, the previous question, just
Mhm.
to see, can you show the options once again?
Okay. These are options.
So that fourth option, by the RHP 0, what variables reduce the phase margin? Is it mean if the RHP 0 moves closer to imaginary axis or it is moving far away from?
Oh, no, like what? How I was looking at it is the RHP0 is there. What it does, it reduces the phase. It never increases the phase. Right? If the RHP0
Okay.
moves or changes also, it does always, it will add a negative condition to the phase. Right? So the RHP0 will always reduce your phase margin.
So that option is correct.
Yes, so RHP0 will
Then
reduce.
then third option, smaller DC gain means body plot will shift downwards. So phase
Yes.
margin will increase.
Yes,
So that
exactly.
is not correct.
Yes, so smaller DC gain is not correct. So C option is not correct. High input
B is
voltage.
high input volt. Body
Yes.
plot will move upward. Gain
Yes.
crossover frequency will increase and phase margin will decrease.
Correct, correct, correct.
And then A option, high sawtooth voltage means that FM will that is
Reduce.
coming in the denominator. So DC gain will decrease.
Yes.
So phase margin will increase.
Yes.
So phase margin reduces in RHP 0 case and
High input voltage.
high input voltage case. So B and D are correct.
Yes.
Okay, sir. Thank you.
Yeah. Okay. Okay. So any other queries you guys have?
Sir, in the previous week, there was something related to that uh, impedance stability. One equation.
Okay. Which
I
equation?
forgot the name of that. Some ZD and ZN was coming. So can you briefly tell that one or two points?
Mhm.
Some
Right.
when we are considering the output impedance of that source, sir has shown uh, one formula for
Yeah,
1
some
plus Z out by
is out of S by Zn of S. 1 plus S set out of S by ZD of S, right? This is your middle
yes, yes.
extra
Yes, yes. Middlebrooks extra element theorem. Yes, yes. So
element.
physical meaning of that. Why? What is the use of that?
So basically, we are trying to understand what is the impact of your EMI filter or your input filter on your control to output transfer. So this is your factor. Like let us see your original GVD of S for a buck converter. It is V in upon ideal case, V in upon 1 plus S upon Q omega naught plus S square upon omega naught square, right? And this Z out of S, is it Z out of S or Z in of S, right? Should be Z in of S if I'm not wrong. Z in of S. That is the input impedance of your buck converter. So this is your original GVD of S. Now when you introduce this filter, what does the filter see? It sees your input impedance. Oh, I think I'm making a mistake here. How does it look like? Let us see. So you have your input voltage, then you have your filter, then you have your DC-DC converter. So when these two interact, this Z out is seen over here, this Z in is seen over here. Okay. So your GVD modified 1 is given by 1 plus Z out of your filter by Zn of S upon 1 plus Z out of S by Zd of S into your original GVD of S. Okay. Z out of S is your of this filter. Now Zn of S is your input impedance when your V output perturbation is 0. And Zd of S is, if I'm not wrong, it is the denominator of your input impedance. Zn of S under some certain case. So that case I can't exactly remember. But so what this theorem says is we have to also consider this overall expression, and we have to check whether our stability gets changed, whether stability gets affected. Okay.
Okay, sir. So Z out is corresponding to source output impedance of that filter
Yes,
source
yes,
side,
yes, correct, correct.
and the Zn and Zd are for the converter.
Yeah, for the converter. There are certain conditions. I think output voltage perturbation 0, Zn of S is for some other particular condition, but I don't exactly recall.
Okay.
Them. Yeah.
Okay, sir. Okay.
Okay. Then any other queries? Okay, if there are no other queries, then we can end this session. So thank you for joining. It was very interactive. I really enjoyed it. Yeah. So again, my sessions are shifted to Tuesday and Teja's session will be shifted to Monday. The recording you will get it soon. I'll upload it on my channel. The link of that I'll put it. So this is a link to my channel. Over here, I will be uploading the video. Okay, once I finish editing it and upload. Okay. So thank you everyone. I'll end the meeting.
Okay, sir. Thank you, sir.